Hi again. So now the focus is on you learning all about the principles of radiation protection. You may already know something about them. And these are the main objectives for today's lesson. We're going to summarize the principles. We're going to name international and national bodies responsible for safety. We're going to describe the role of each individual member and their responsibility. And we're going to list the Bonn Call for Action aims. There are 10 of them. And we're going to discuss those. And we're also going to discuss ethical considerations that impact radiation protection. So the fundamental safety objective is to protect people and the environment from harmful effects of ionizing radiation. And this applies to all circumstances that give rise to radiation risk. And those circumstances will include medical, occupational, and public exposure. Medical exposure, of course, refers to exposing patients to radiation for the purpose of treatment and diagnosis. Occupational exposure refers to the radiation exposure received during the course of our regular and daily work. Now, this slide comes from the International Atomic Energy Agency, its basic safety standards. One of their roles and responsibilities is to address all situations involving radiation exposure that is amenable to control. So I want to focus your attention for a moment on pressing issues in workplace and public safety. In the workplace, exposure can occur through the use of radioactive sources, the use of radiation X-ray machines in medicine, and the use of X-ray machines in scientific research. Do you know anybody that works in the agriculture or the industry sector? Well, working in agriculture and industry may also involve handling of materials containing high concentrations of naturally occurring radionuclides. Adequate radiation protection of workers is essential for the safe and acceptable use of radiation and radioactive materials and nuclear energy. Have any of you heard of blue asbestos? Blue asbestos is considered by many to be the world's most dangerous mineral, or naturally occurring mineral. Exposure to it can cause fatal diseases, including lung cancer. Asbestos mining occurred mostly in West Australia and Bolivia and South Africa in the past, and production has ceased since because of the many health issues that occurred. But in an area in Western Australia where the blue asbestos mining was carried out between, I think, 1940 and 1960, around about that time, more than 1,000 miners and residents died of lung cancer and other diseases caused by mining of the mineral. In those days, blue asbestos was commonly used to insulate steam engines and pipes and was part of plastics and cement products. And then there's another well-known mineral, which is white asbestos, which is still a problem in the United States today. It is commonly used and can be found in the roofs and ceilings and walls and floors of homes and businesses and even schools. If a school was built before the 1980s, it's likely to contain some form of asbestos. When the asbestos starts to wear down or degrades, it puts students and teachers and employees at risk of asbestos exposure. And similar to the blue asbestos, it can result in lung cancer. Protection is therefore key to safety. And the ICRP, International Commission on Radiological Protection, they define the three basic principles of radiation protection. And those three principles are justification of practices, optimization of protection by keeping those exposures as low as possible, and then dose limits for occupational workers. The protection level is considered based on the idea that risks cannot be completely eliminated, and on that assumption, the risks should be tolerated. This is the very basis of the principles of radiological protection, placing emphasis on the justification, optimization, and the application of dose limits. The principle of justification refers to radiation exposures doing more good than harm. Radiation exposure should always be kept at the lowest possible level. However, when illness or injury occurs, a patient may decide to assume the relatively small risk of exposure to ionizing radiation. The risk they assume is meant to be for their benefit. Hence the phrase we are all familiar with, which is benefit versus risk. Remember that from patient care? The next key term or key principle is optimization. ALARA is an acronym for as low as reasonably achievable. Now, this term is synonymous with the term optimization for radiation protection. The intention of these concepts is to keep radiation exposure and consequent dose to the lowest possible level. So radiation-induced cancers do not have a fixed threshold, that is, a dose level below which individuals would have no chance of developing this disease. There is no such thing, okay? Any level of radiation could potentially cause cancer. There is no threshold. Therefore, it appears that no safe dose level exists for radiation-induced malignant disease, and radiation exposure should therefore always be ALARA for all imaging procedures. The ALARA should serve as a guide to the radiographers and to the radiologists for the selection of the correct technical factors to use and the correct examination. And then the last key principle is limitation. With limitation, individuals working with radiation must be protected to limit and prevent any undue harm. So dose limits are prescribed for workers and for students and for the public. For example, for myself as a worker, I can only receive up to 20 millisievert per year. For yourself as a student, the recommendation is 6 millisieverts according to the Hamad Hospital. Other regulations in the ICRP often state 1 millisievert for a student, the same as the public. And we know that the public dose is 1 millisievert. So, do you know if dose limits apply to patients as well? Any thoughts on that? Well, the answer is that dose limit is not applicable to patients undergoing diagnostic or therapeutic procedures. The exam is what we refer to as being justified because it does prove to be more beneficial than providing a risk to the patient. So how can we go about applying these basic principles? What actions can we take? So here are some cardinal rules, also often referred to as basic principles or actions of radiation protection. These are simple things that can be enforced for our protection and the safety of our patients, and that is time, distance, and shielding. We have to always try our best to reduce the amount of X-ray beam on time. We have to use as much distance as is warranted between the X-ray tube and the patient for the examination, and we always have to shield whenever that is possible. So what do I mean by radiation on time? Well, occupational radiation exposures of imaging personnel can be minimized by the use of these cardinal principles I mentioned before, by shortening the length of time spent in the room when the X-ray is being produced, by standing at the greatest distance possible from the energized beam, and by interposing a radiation shielding material between the radiographer and the source of the radiation. So in reality, X-ray techs are only exposed to a small fraction of the dose limit for workers, which is 20 millisievert. It's important, though, to recognize that most doses are represented in standardized international units. That's what's used globally these days. However, traditional units are still recognized and are used by some places like the United States. So it is best for you as the current generation of radiation workers to understand both the metric system and the traditional system of safety measurement. For our purposes right now, I'm only mentioning the SI unit of absorbed dose, and that is the gray. When you multiply your absorbed dose by a value or a weighting factor given to the type of radiation you're dealing with, in our case it's X-ray, then you get an equivalent or effective dose that is represented in the sievert or in the millisievert. We will be looking at this more closely in one of the other units, so don't pay too much attention to this right now. So these are typically the type of exams you will be dealing with in the radiology department. And there are two types of radiation effects we commonly refer to, which is stochastic and deterministic effects. Now, stochastic is long-term effects, and deterministic is short-term effects like erythema, reddening of the skin burns, cataracts, and so forth. So do you think it's possible to get deterministic effects in our line of work? Well, I'm happy to report that this is highly unlikely that these types of effects will occur. So even though our risk is relatively low, we still have to have radiation procedures and protocols in place. Now this image captures the international organizations that are responsible for radiation protection and enforcing those rules and regulations to protect ourselves and our patients. So every year, a large number of reports on research concerning radiation are publicized by researchers worldwide. Now, the United Nations Scientific Committee on the Effects of Atomic Radiation, I know that's long-winded, basically UNSCEAR, they comprehensively evaluate wide-ranging research outcomes, and then they compile a scientific consensus. And this is obtained internationally, and is usually a neutral standpoint. And then they periodically release a radiation safety report. Once this report is released, the ICRP comes into effect. The International Commission on Radiological Protection then makes recommendations concerning radiation protection frameworks while they are referring to reports produced by the UNSCEAR. So next in line is the International Atomic Energy Agency. And they have a document called the Basic Safety Standards, which many countries ascribe to. They establish a comprehensive document, and this document refers to ICRP recommendations, and it is referenced back to the scientists that are part of the organization, the UNSCEAR organization. Basically, they compile all of the safety information, and then they provide that to organizations worldwide. For example, the government of Qatar has formulated its laws and its regulations and guidelines based on the basic safety standards of the International Atomic Energy Agency. So out of all of these international organizations, the ICRP and the IAEA basic safety standards is what we need to pay close attention to on a regular basis. This will ensure that our knowledge is up to date and current with regards to the safety regulations. The ICRP and the IAEA publications are readily accessible online. The ICRP publication 103, for example, this defines the process of justification, optimization, and limitation, and it is a free resource online. All you have to do is sign up. The IAEA, on the other hand, has free educational resources such as PowerPoints, and these PowerPoints you guys could easily use for assignments or as a reference for your assignments. The safety standards, or the basic safety standards that comes out of the IAEA, is a highly reliable source of information, as it serves as a global reference for protecting people and the environment from radiation worldwide. As an example of the importance of the ICRP are these recommended dose limits for workers, students, and the public alike. At the end of 2013 or the beginning of 2014, aroundabouts there, revisions were made to these dose limits, and this resulted in a change to the equivalent dose of the eye. So as you can see here, previously the recommendation was 150 millisievert in a year to the lens of the eye, and now that's been reduced to 20 millisievert per year for workers and for students in training. So what regulatory bodies do we ascribe to here in Qatar? Well, the answer to that is the Ministry of Municipality and Environment of Qatar, which is law number 31 to be specific, and the International Atomic Energy Agency. The state of Qatar is a member state of the IAEA Radiation Protection Organization. CNAQ, though, however, goes a step further and not only embeds the Qatar Law 31, the IAEA and the ICRP regulations, but also follows the Canadian Nuclear Safety Commission regulations, namely the Safety Code 35. So what do all of these radiation safety documents and standards, what do they contain? Well, they contain things like who's responsible for what is the manager responsible for, what is the licensee or the safety officer responsible for, what are the conditions of service, how do you practice and how should you practice, what are the local rules, what are the rules regarding protective equipment, what are the rules regarding monitoring and workplace safety, and how about maintaining records? Now, before we delve into all of this, I want us to take a quick break. I think we've been going for long enough now, so let's take a 5 to 10 minute break before continuing on with the second part. Okay, chat to you guys soon.